Diamond and graphite are two pure forms of carbon that we know of. In fact, graphite is the material in pencils. Now, if you look at the material that's in graphite, you'll find that it's made of carbon atoms that form hexagons. And you can see that on a model I've got here. So these are six-sided rings, and these join together to form sheets of hexagons. So presumably, when you draw with a bit of pencil, sheets of these atoms are coming off onto the paper. Now you can see that the hexagons is very flat. But if you can take a hexagon, 1, 2, 3, 4, 5, 6, and make this into a pentagon with 5 atoms, it will curve the sheet. And actually you can do this if you heat graphite to very high temperatures, 2,000–3,000 degrees centigrade, then sheets and atoms will come off and they'll reform into structures which have pentagons and hexagons in there. And that's what we do when we make C60. This is a beautiful round carbon cage molecule called C60 or Buckminster fullerene. And it's a molecule containing 60 atoms, and you'll see that it's got hexagons on the structure, but it's also got pentagons. And it's got the same shape as a football. And in fact, if I show you the football, it shows up the structure really rather well. You see that you've got black pentagons on the structure, there's 12 of those, and there's also hexagons. And it turns out, and it's amazing, but you can curve up any size hexagon sheet, apart from one hexagon, if you just put 12 pentagons in. So you can have thousands and thousands and millions of hexagons, and they're flat. But if you put just 12 pentagons in, it will roll it up into a cage. So C60, it's where all the pentagons are separated by one edge. I've shown this on this model here. So we've got a pentagon here, one edge, and then another pentagon. The hexagons can be side by side, but the pentagons are all separated by one edge. And you can make larger structures. There's a beautiful one behind me here. And again, this only has 12 pentagons in it, but it has many, many more hexagons, as you can see. And where the structure tends to curve is where the pentagons are. So there's a bit of curvature here. There's a pentagon here, and there's a pentagon here. Now, there's a nice rule for working out how many atoms are in these structures. It's called the 60n squared rule. What does that mean? Well, it's the number of atoms is given by 60 times the number of edges squared. So if we take two adjacent pentagons and we count the number of edges, in the C60 molecule there's only one. So the 60n squared rule will be 60 times 1 squared, which is 60 times 1, so that's 60. So how many atoms on this giant one? Well, we've got one pentagon here, the next adjacent pentagon is here, so we've got 1, 2, 3, 4 edges. So 60n squared will give us 60 times 4 squared, which is 60 times 16. So this has got 960 atoms in this structure. So C60 is actually the head of a family of structures. This is called Buckminster fullerene. It was named after the designer and architect Richard Buckminster Fuller. And the whole family of cages are called the fullerenes. And this is an example of a giant fullerene. So this is C960. And these form a whole range of interesting new carbon structures. They may explain soot, for example. When you put toast in the toaster and you turn it on for too long and it burns, those black particles are spherical carbon particles. And it may be that they're cages within cages within cages, something closely related to these giant fullerenes. So this may help us to understand soot and those sort of structures. There are even stars in space spewing out tons and tons of carbon dust into space. And these giant fullerenes may help us to understand particles in space as well. So these are the giant carbon fullerenes.